Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. This is primarily for chemistry, but it would also apply to physics if you want to do a review of thermodynamics. So once again, I've sketched the heating curve here, and you should be pretty familiar by now with this curve. Energy increasing to the right, temperature increasing up the y-axis, and substances begin in the solid state. I add energy, they warm up, but they reach a point where they melt. Here in the solid state, we use the specific heat in the solid state to do calculations. To melt it or freeze it, we deal with the heat of fusion. In the liquid state, we use the specific heat in the liquid state. To boil it or condense it, we use the heat of vaporization. And then we use the specific heat in the gaseous state for calculations up there. In an earlier episode, I had done calculations in just one of these three phases, solid, liquid, or gas, for one substance. In a later episode, I'd done calculations of just melting or condensing or boiling or freezing, so just one of these horizontal lines for one substance. In this exciting episode, I'm still remaining with just one substance, but what I will do is calculations for multiple phases on the heating curve. So not just one diagonal segment, not just one horizontal segment, but a combination. So at first, I thought I was going to do acetone, so I didn't have the right amount of data. Then I switched it to aluminum, realized I didn't have the heat of fusion that I needed for it. So now, copper. On the reference sheet, we have enough information about copper that we can work through an example problem. So I'm going to take a mass of 175 grams of copper. We can forget my failed previous attempts. And I want to start in one phase. So I see copper has a melting point of 1085 degrees Celsius. So I'm going to go below that and say my initial temperature is 1000 degrees Celsius. Copper's boiling point is at 2567 degrees Celsius. And I don't want to go that high. So looking at what I just put in here, I want to go to, let's make it 2000 degrees Celsius. So in this situation, I will be starting with copper in its solid state, heat it up to its melting point, melt it, and then heat it up, but not as high as its boiling point. So on the heating curve, I'm starting with solid. You can't see that. I'm starting with solid copper. I'm going to heat it up. That's one calculation. I'm going to melt it. That's the second calculation. And then I'm going to heat the melted copper. That's the third calculation. And mathematically, we just do each one of these three calculations and add them together. There's the total. There's the heat energy for this problem. Simple, but I thought you'd like to work through a couple of examples, right? So here we go. First, I need to heat up the copper. It's in the solid state. Its mass is 175 grams. I look up the specific heat of solid copper, and I see it listed as 2. Sorry, reading the wrong thing. It's 0.385, 0.385 joules per gram per degree C. Now, it would be a mistake to say that the final temperature is 2000 degrees or that the delta T is 1000 degrees. Those are both wrong because I can only go up the heating curve until I get to its melting point. So the final temperature for this calculation right now is 1085 degrees Celsius. And subtract from that my initial temperature of 1000 degrees Celsius. So I'll call this Q1. The heat energy necessary to heat up solid copper to its melting point. Q2 will be the heat energy necessary to melt that copper. It's the mass of that copper, 175 grams, times the heat of fusion for copper. So on this chart, it says the heat of fusion is 205 joules per gram. So multiply by 205 joules per gram. And that will give me how much heat it takes to melt 175 grams of copper. But I'm not done. Now that I've melted the copper, I do a third calculation. And for this one, I take that mass of now liquid copper and I heat it I heat it using the specific heat of copper in the liquid state, 0.490 joules per gram per degree C, times the change in temperature. Now, the final temperature is going to be 2000 degrees Celsius. The initial temperature is not 1000 degrees Celsius, it's the melting point of copper. So I'm beginning with melted copper, and that's at a temperature of 1085 degrees Celsius. I now have my three heat calculations, and the total heat energy it takes to do this problem is the summation of the heat energies for each of the individual steps. So you can go ahead and calculate it, beat me to the punchline. By the way, mathematically, the distributive property applies here of multiplication. So I could factor out 175 grams from each of these three heat calculations and do this sort of almost in one step on your calculator, right? So I'll do it that way. 175, open parentheses, 0.385 times 85, you could do that one in your head, plus 205, so that's Q2, plus 0.490 times, and this one, I suppose I could do it in my head, it's 85 degrees less than 1,000. So that would be 900, 915. Did I do that correctly? 915 plus 85 would be 1,000. Okay, close parentheses, enter. Beep, beep, beep. No doubt you got the same result. I got 120 kilojoules. That is the total heat energy that I calculated to take copper in the solid state, heat it up, melt it, and then heat the liquid up to 2000 degrees Celsius. Okay, so that ends example one. I want to work another example or two, right? So let's take ammonia. Next page. And okay, I'll start with the mass of 325 grams and an initial temperature. See, I'm getting clever. I wrote this down just ahead of time. Hopefully it's going to be correct. I'm going to start with an initial temperature of negative 70 degrees and take it up to a final temperature of 0 degrees C. Calculating, please. In this case, sure. How much heat energy will it take to do that? So go ahead and pause, calculate it first, beat me to the punch. As I try to do this, I see that ammonia is a solid up until it gets to negative 78 degrees Celsius. And I'm starting at negative 70 degrees Celsius. So it's starting in the solid state. So first I'm going to have to heat the solid. its final temperature, remember this is ammonia, not water. So ammonia boils at negative 33 degrees Celsius. I'm sorry, I said something wrong here in the first place because I'm negative, right? I goofed. Ammonia at negative 70 degrees is hotter than ammonia at negative 78 degrees, right? So I goofed when I said it was in a solid state. It's actually starting off in a liquid state, a little bit, well, 8 degrees above its melting point. So it begins in the liquid state. And what I'm going to do is heat up that liquid. The boiling point for ammonia is negative 33 degrees Celsius. So I'm going to have to vaporize the ammonia. So I need a delta H of vaporization. And then in the gaseous state, I need to heat it up to 0 degrees. So there are going to be 3 calculations here, just like the previous example. Previous one went solid, melt, liquid. This one goes liquid, vaporize, gas. Nothing else changes. So Q1, I'll call it, would be 325 grams. And I'm sorry I didn't give you a density conversion to do along the way. Maybe someday. Times the specific heat of liquid ammonia. The chart says specific heat of liquid ammonia is 4.700 joules per gram per degree C. Now, the increase in temperature is going to be from negative 70 degrees initial temperature, but not to 0 degrees. I can only heat liquid ammonia to its boiling point. So I can only increase it to negative 33 degrees. So final temperature is negative 33 degrees, and I subtract from that its initial temperature of negative 70 degrees C. Yeah, how good's your math, right? So a negative number minus a negative number really means a negative plus a positive. Nice to know. So that'll be Q1. Q2 will be the energy necessary to actually vaporize this ammonia. So the quantity is 325 grams. And now I look up the heat of vaporization of ammonia, and it says 1,360 joules per gram. So 1,360 joules per gram. That will give me gaseous ammonia at its vaporization temperature, boiling point. Last step is to heat up that gaseous ammonia. All 325 grams of it are now going to be heated using the specific heat of gaseous ammonia, which is on this chart, 0.261. Sorry, you can't see it. I said that incorrectly. 2.061, my bad, joules per gram per degree C times the change in temperature. Now, the final temperature is 0 degrees, but I'm not starting at negative 70. I'm starting at the boiling point of ammonia. So I'm going to subtract negative 33 degrees C, right? And so really the change in temperature is going to be 33 degrees C. Okay? Just like the previous example, the total energy is going to be the sum of these individual energies. You can use the distributive property of multiplication to factor out the mass and then do that outside the parentheses. So I go 325, open parentheses, 4.7 times 70 minus 30 is 40. So this should be 37. In other words, negative 30 minus negative 70 should be 537 degrees Celsius plus 1,360 plus 2.061 times 33, close parentheses, enter, beep, 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 and I end up with 521 kilojoules total energy in this example. Oh, but let's not stop there. Let's do another example. Please, Mr. Turk, please. So I scribbled down that I was going to do iron. So here's the next example. I've got iron, and I said, let's start that one at 1500 degrees Celsius. And let's take that up to 3000 degrees Celsius, making me wonder if I am doing this correctly. And I'm going to use a total energy to do this. Wow, this seems so small. 4,500 joules of energy is all I have available. I need to start here and end there. And so therefore the question becomes, how much mass can I use that starts here and ends there? So off to the valuable reference table. And for iron, I see its melting point is 1,538 degrees. So I'm beginning in a solid state. The boiling point of iron is 2,862 degrees. So I'm making the same conceptual mistake I made with copper, because I don't have the specific heat of iron in the gas state. I need to create a problem that doesn't go into the gas state. So at most, I could vaporize this iron and have it in the gas state at its boiling point. So let's do that. Let's go all the way to gas at its boiling point, which would be 2,862 degrees Celsius. And here's my new problem. Let's go figure it out. So the unknown in this problem is going to be the mass, not the total energy. We're starting in the solid. I have to heat the solid, so that'll be Q1, heat the solid. Then I have to melt the solid, so that'll be Q2. Now it's in a liquid state. I need to heat the liquid to its boiling point, and then I get to vaporize the liquid and turn it into a gas at its boiling point. So I have 4 heat calculations. For the first one, it's going to be the unknown mass times the specific heat of solid iron, which is 0.450. 0.450 joules per gram per degree C times the change in temperature. So I'm starting at 1,500 degrees. Its melting point is 1,538 degrees. So in my head, the change in temperature is going to be 38 degrees Celsius. This will get my solid iron up to its melting point. Next, I need to melt this iron. So I look up for iron. The heat of fusion is listed as 266 joules per gram. 266 joules per gram. I've now melted my unknown quantity of iron. Now I need to heat that liquid iron to its boiling point. So the specific heat of liquid iron is 0.820 joules per gram per degree Celsius. And the change in temperature is going to be the boiling point, 2,862 degrees Celsius, minus its melting point. because we're not starting at 1,500 degrees, we're starting at 1,538 degrees. All right, so that will get me that'll get me boiling point liquid iron. And now the last step will be to actually vaporize this. So the unknown mass times the heat of vaporization for iron, which is 6,290 joules per gram. Okay? When I add together these four different energies, I'm going to get a measly 4,500 joules, which is not a lot of heat energy compared to the previous problems, right? I had 500 kilojoules. Now I'm talking about less than 5 kilojoules. Oh, well, it's a made up number. But there is an answer for it. So there will be some quantity of iron, and it might not be very much, but it will be some non zero mass that we can calculate. So you look at this, and it might be a little intimidating, but there's only one unknown, and this is a math 1 type problem. Solve for m. It's the only unknown. So what you can do is factor out the mass and say m times, I'll do it in square brackets, open square bracket. The first one is 0.450. I'm going to do this quickly and not write down the units. Times 38. The next one is, so that's the first one. Now go plus, m is factored out, so 266. Plus, for the next one, m is factored out, and I have 0.820 times this difference, which I'm not going to do it in my head, although it's somewhat tempting. I will do this much by calculator. So I'll go 2862 minus 1538, enter, and I get 1324 plus 6,290. Close square brackets, and all of that is set equal, which you can't quite see, equal to 4,500. Okay, so boop, there you go. You have one unknown, solve for m. So m is going to be 4,500 divided by everything that's in those square brackets. So 4500. You can beat me to the punchline. Beep, 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 beep. And sure enough, I don't get much. This is less than 1 gram. 0.588 grams to 3 significant digits is the total amount of iron that I could heat from 1,500 degrees to 3,000 degrees. Now, if I were to just add a 0 to Q here at the beginning and say, oh, did I say 4,500 joules? Let's make it 45,000 joules, right? If I were to add a 0 here, then I get to move the decimal one place here as well. So that would make it 5.88 grams. So that part's linear. Okay, I did want to, I think, try one more example. No, you do this. So here, let's do a practice one for you. Water, your favorite substance. Calculate, please. For water, if I start at negative 10 degrees Celsius and I heat that water, ooh, how much? How much? I wrote down some random number. Okay, so that's the initial temperature. And I'm now going to heat this water to a final temperature of 80 degrees Celsius. And I think I decided I was going to have you solve for mass this time. Yeah, okay. So again, to celebrate all those seniors among us, I have a heat energy of 2,020 joules. Calculate, please, how much water can I take through that temperature change? So the problem, once again, I have water at an initial temperature of negative 10 degrees Celsius. I want to heat that water to a final temperature of 80 degrees Celsius. And to do that, I'm going to use 2020 joules of heat energy to do it. Calculate, please, how much mass does it take to do that? All right, I'm kind of tempted to pause this because you should be pausing it too. So, sure, pause like me. Okay, well, I'm done. No doubt you're done. So you realized you had to heat up solid water to its melting point. Then you had to melt the water. Then you had to heat the liquid water to its final temperature, and all that rearranging and solving for the mass. So the answer I got was 2.93 grams. This concludes this educational video. Ciao.